Today we're going to talk about something that is perhaps the subject that many of you will wind up discussing more than anything else from the entire semester. So, don't shout out any answers. I just want to take a survey. Okay. Roswell, New Mexico, 1947. How many people know what I'm talking about? Raise your hands. Look around, the rest of you. Hands down. If you didn't raise your hand now, so we'll know how many of you don't know what I'm talking about. Okay, there are a few. Roswell, New Mexico. The newspaper in Roswell, New Mexico on 1947 had an interesting headline. It said that the United States had captured a crashed flying saucer. The headlines, the copy of the newspaper, if you go to the HTML, the web version of the textbook, there's a link there, and you can link and see the headlines for the flying saucer crash in 1947. Interesting history to this as you look back into it. The United States announced that they had recovered some flying discs. The newspapers reported this. Flying saucers captured, Roswell, New Mexico. The next day, the U.S. Issued a correction. They had not captured or recovered a flying saucer at all. In fact, all they had recovered was a crashed weather balloon. Anybody who had been at the site or had seen photos of the site, there's been a lot of people like this, knew the U.S. government was lying. 1995, the U.S. government officially announced that, in fact, in 1947, they lied. They lied on purpose. They lied because they did not want the people of the United States or the people of the world to know one of their most highly classified military secrets. So today I will tell you what really happened in Roswell, New Mexico in 1947 about the military secret. It is no longer classified, but it's a little bit different than many people thought. So we'll talk about what happened there. As a prelude to that, because a key character in the 1947 events was a physicist named Maurice Ewing, who you may not have heard about. Maurice Ewing. At the beginning of World War II, he was studying the oceans, and he came up with a rather amazing discovery, which was one of the most classified aspects of World War II. And based on that discovery, he came up with an extremely clever invention. And let me tell you about this invention, just to present it as a mystery. Imagine how useful this is and how difficult it is to figure out how it works. Imagine you're the enemy, for example, and you capture an American pilot who was shot down over the Pacific. In his emergency kit, he had these spheres. They were called SOFAR spheres. S-O-F-A-R, SOFAR spheres. And his instructions were, if he gets shot down over the Pacific, to drop one overboard. And then wait. If nothing happens, if 8 hours later nobody has picked you up, you drop another. Now this is the Pacific Ocean. And let's say you're on a mission where you got thrown off by a storm, or maybe someone was chasing you, and you're hundreds of miles from where anybody expected you to be, and you get shot down, and here you are in the ocean, and your instructions are, open up your emergency kit, there's some extra water in there, a little bit of food. Don't send a radio signal, because if you send a radio signal, the enemy might pick it up and know where you are and go and capture you. Instead, drop this sphere overboard. And if you do that, a few hours later, the planes will come and pick you up. This was the invention of Maurice Ewing, the SOFAR spheres. And they're related directly to the events of Roswell, New Mexico in 1947, because that was also a project of Maurice Ewing. It was a project that he invented based on his success with the oceans. And in both cases, it has to do with the movement of waves. Let me just give you the so far story right away. These spheres, if you found them, if you were the enemy and you learned this, and here's this guy and he said he's supposed to drop these overboard, and you have one, and say, well, let's see how it works. So you cut it open and it turns out it's a hollow metal sphere with nothing inside, just big empty space. That's it. How could that work? What Maurice Ewing had discovered was deep down in the ocean, there was a phenomenon that we now call the sound channel. And here's how it works. Sound channel became known after World War II. It became one of the key elements of the Cold War between the US and the Soviet Union. It became the central bit of physics in submarine warfare. How many people here have read a book called The Hunt for a Red October? How many people here have seen the movie? The book and the movie are quite different. The movie is sort of an adventure movie. The book is the first techno-thriller, and it describes in great detail the sound channel. We're going to be talking a lot about the sound channel and how sound moves and the essence of the sound channel for the whole flying saucer story. So the sound channel is under the ocean. There are actually two sound channels that we'll talk about. The first one is under the ocean. And here's how it works. Sound, when I talk to you, what happens is my sound goes away. Well, you're hearing me through this. I should take it off so that you get the sound directly. That's what I'm referring to, but let me use the microphone. How do I communicate to you using sound? The answer is I force air up through my throat. In my throat, there's a piece of skin called the vocal cords. As I push air through these, the skin vibrates. It's sort of, what's a good example? When you push something, it makes them vibrate back and forth, and that makes the air vibrate. So by pushing the air through these vocal cords, they start vibrating. They make the air vibrate. When the air starts vibrating, it pushes on the air next to it. Makes that air shake. That pushes on the air next to it, that makes that air shake. The air doesn't actually go from me to you, but the shaking does. Let me give you, here's a similar thing. This isn't air. Let me just take this off. I love this thing. It's a bunch of wires all hooked together. If I shake this one, it twists the center wire a little bit. That twisting center wire makes the next one start moving. That twists the wire next to it, makes the next one move. So if I move this one up, look at that. This one is moving up and down. The next one is moving up and down. But what you see moving is the energy. The energy is being transferred. None of these things is moving sideways, but you see that. Here's another one. If you haven't played with slinkies, now's your opportunity. Go buy a slinky. Here, could you hold the end of that? Okay, slinkies, wonderful things. If you haven't played with slinkies, you have a disadvantage in this class. Go out and buy a slinky. Okay? Here's a slinky. Now watch, I'm going to shake the end. Look how the wave goes back and forth. What is a wave? How did I manage to twist this? Every time I do a slinky, I twist it. It's like pair production. It's like pulling two corks apart. I get these two corresponding twists. and then the slinky is ruined. It's happened to me ever since I was a kid. The theorem about anybody know how to untwist a slinky? Look at that. I just did it. I twisted a slinky, and there are 2 twists, and now the slinky is not the same anymore, and Christmas is ruined. I don't know how this happens. Fortunately, we have a fellow here who's very good at untwisting them. I can't do it. Okay. Thank you. In fact, what I want to do is do a better demo all the way across the room here. Now, could you stand up and hold it high? What's going on? Okay. Now, the thing about the slinky is what is moving? What is moving? Well, the spring is moving, right? But watch. I'll suddenly shake it. Wow! And the shake moves across the room. The slinky moves a little bit, but no part of it really moves very far. I can do a compression. And you can see that move. And it bounces. Isn't it interesting how it bounces? Watch this. I'll compress it like this and let it go. Boom. We've seen this before. We've seen it with water waves. Okay, I'm going to let go, and you can... Now that's a moving slinky. Okay, but a wave is something else. It happens to be a rope right here. Okay, you could just put that on the table. Watch the rope. I'm going to make a little shake in the rope. Look at that go. But what's going? The rope isn't moving. Well, it's moving locally, but it's the energy that's moving. It's a way of transferring energy. Same thing here. I shake this one, and the energy gets transferred. It's amazing. This one stops. But the energy gets transferred, and then it bounces off the end. Why? Because the energy has to go somewhere. Look at this wave. We're talking about waves today. That's really what we're talking about. And it comes back, and it moves. Sometimes it's hard to recognize that a wave isn't a thing. It's just the energy being transferred. When people are in the water and the waves come in, that's another thing you should all do. Go out to the beach and go swimming and enjoy the waves coming in. And as the waves come in, you tend to think of them as a thing, don't you? And yet the water really doesn't go very far. Well, at the end, when it comes to the beach, the water may come sloshing in. But out there, if you're in the ocean, it's an interesting thing. Before the wave breaks, when you have that nice rolling wave, it's an interesting thing. You go out there and you float in the water. I don't know how many of you have done this. The water out here in San Francisco is a little bit cool. But if you float in the water and the wave comes by, you know how you go up and down and then you're back? But you're also going forward and backwards. And so as the wave approaches, you find yourself being sucked in. And you're getting low because it's a trough. And then as the wave comes, you get up really high. And then you're going forward. And if the wave doesn't break, you'll just go down like that. The fact is, for a water wave, you wind up moving in a circle. It's actually a circle. Assuming it doesn't break. So you should all do this. Go to the beach. Maybe you should go to Southern California where the water's warmer. And go out there beyond where the waves are broken. Because a broken wave is a peculiar case where the thing got so steep that the top actually fell over. But the wave itself, as you go around, you're actually moving in a circle as the wave goes around. We're going to be talking a lot about water waves and tsunamis, which are a special kind of water wave. So this is a wave, but the water only moves a little bit, yet the wave goes on forward. And if you go to a cliff, go along, the California coast is great for this. Go to a place where the cliff is steep, where the water comes right in, waves come in, and you watch them bounce off. You could have the illusion that a wave is actually an object rather than something just moving, rather than the energy moving. But a wave is actually just the energy moving. Now, as we get to relativity theory, we're going to start asking, what's the difference between energy and mass? And in relativity theory, it's going to turn out there really isn't any difference. And so when I say the energy is moving, well, is there mass moving down like that? Relativity theory, which we'll get to near the end of the semester, will say, yeah, there's mass moving, right? Energy and mass. So a wave is traveling energy, but in some sense it's also traveling mass. But there's something that's carrying the wave. In this case, it's the string. In this case, it's this peculiar construction of wires and things. I like this just because it travels slowly, so you can watch it. And then it bounces. Comes back and it bounces again. And so this wave travels super fast. Interesting thing here. This is a key feature of waves. Surprises a lot of people. Suppose I make a little wave here. Little wave. Ready? Boom. There it goes. Okay. Now I'll make a big wave. Whoomp. There it goes. Now which one traveled faster? In many cases, they travel exactly the same speed. Suppose I make a very low frequency wave. There's the wave. Make a really high frequency wave. Frequency is how fast the wave vibrates. Here's a high frequency wave. Yeah. The high frequency wave and the low frequency waves travel at the same direction, at the same speed. Interesting. That turns out to be really important for sound. When I'm speaking, my voice is a combination of low frequency and high frequency mixed together to make my voice. When you're singing, you go from low, whoa. But the sound velocity is the same for all of those. Most peculiar. Works out that way. If it weren't for that, when I talk to you, you'd understand me when you were close. But if you were far away, you'd have trouble understanding me because the high frequencies would take longer to get to you or shorter. For sound is also a wave. It's a wave where I make the air vibrate here, that makes the wave vibrate here, makes it vibrate there, and so on. Now, if this air kept on vibrating, by the time it got to you, there'd be no energy left because all the air in between would be vibrating. But a wave doesn't work that way. A wave transfers the energy to the next atoms. Rather amazing thing. And so when the signal gets to you, it's enough to vibrate the thin membrane of skin that's in your ear. It's called the eardrum, right in here. And that thin membrane of skin, this is an awfully thick-looking eardrum. Oh, this is the bone. See, that's the bone that holds the eardrum. The eardrum is actually this thin layer of skin. That thin layer of skin then pushes against a little bone. Actually, there are 3 little bones here that then take the vibration all the way into the liquid of the inner ear. And that makes the liquid vibrate. The vibrating liquid makes little hairs on the inner ear vibrate. And these little hairs are connected to nerves. When they vibrate, the signal becomes an electrical signal that goes into your brain and you hear it. So we're transferring air coming through my vocal cords. I can control my vocal cords by making them stiff, or loose. Get different frequencies as the air goes through. That makes the air vibrate. The vibrating air comes all the way to your eardrums. Eardrums vibrate. They go against these bones that go into the liquid, that go into the nerves, the little hairs, and then you hear the signal. And this is how we communicate. And the complexity of the control that I have over my vocal cords is such that I can actually convey information to you by using this method. Rather amazing. So this is sound. Sound is a wave. We're sending the energy. But think how easily you can be fooled. You might think this was a thing if you didn't see the rope too well. The fact is, we all are fooled. Because this piece of chalk, everything, according to the theory of quantum mechanics, everything is really just waves. The reason balls bounce is because waves bounce. Atoms are waves. The electrons are waves that move in circles around the nucleus, which is actually a wave that's confined to a very small region. Waves can move in circles. They can go around the Earth, for example. You can have a wave going around the Earth. In quantum mechanics, what we have discovered is that everything is a wave. That is the essence of quantum mechanics. That's one of the reasons why you really want to understand waves, because modern physics, built on quantum mechanics and relativity theory, is basically saying everything is waves, and if you understand waves, you'll understand quantum mechanics. And the difference between quantum mechanics and the things that our intuition all comes down to the fact that electrons, protons, atoms are really waves. When you understand that, you understand the mysterious features of quantum mechanics. For quantum mechanics, what's waving? Here the rope is waving, right? Or the water is waving, or the wires are waving. What's waving in quantum mechanics? Well, this is a little bit of a paradox. Because the waves are what we call things. Here, if you're looking at the wave on this rope, and suppose you were made up of rope waves, and the universe is filled with ropes, and there are these rope waves moving along, and the rope waves get really complicated, they get to talk to each other, and they say, well, okay, I'm a wave, you're a wave, what are we made out of? And someone says, we're made out of ropes. You're a wave traveling on rope. What's a rope? A rope is the thing you're traveling on. You're the wave on the rope. I've never seen a rope. Of course you haven't seen a rope. The only thing you've ever seen are the waves. The only thing you have any familiarity with are the waves. Ropes aren't waves. They're something else. But waves only sense other waves. This is the problem we have when I say, what is waving? When we have an electron. The thing that's waving is something. We can give it a name. We can call it a rope. We can call it the ether. It used to be called the ether. Spelled funny so you wouldn't confuse it with the chemical ether. A-E-T-H-E-R. British spelling. Some people call it the vacuum. Two U's. Must be vacuum. That's what's waving. But what is the vacuum made out of? Now you have to remember, when we think of things are made out of, we think they're made out of electrons. We say they're made out of protons. We're really talking about they're being made out of waves. The vacuum isn't made out of waves. The vacuum is the thing that waves. It's not made out of any material. It is the thing that waves in quantum mechanics. So getting a little bit abstract here, let's get back. We'll return to this. I like to introduce quantum mechanics now because, one, it motivates you. I really want to know about waves. Waves by themselves are one of the most fascinating things. They have this peculiar property, very unphysical property, that they carry energy. Last week, many of you felt an earthquake wave. The way an earthquake works is you have a little bit of ground, and there's a force between the rocks because maybe they're being pushed like this, but they're not slipping. And the force gets stronger and stronger, and finally goes yonk, and it slips. And that may take place 5 miles underground, and when it does, it causes the ground to shake at that location. And that location may be small. Typically, for last week, it was. Exactly how big it was? Probably not more than a few hundred yards. A little piece of the rock deep underground shook suddenly because the rock suddenly, there's friction holding it together, and it slipped. Typically, there's already a separation between the two. That's called a fault, separation in the rock. But they're being pushed together by the pressure of all the weight above them, and so there's a lot of friction. But if one rock on one side is slowly getting twisted and the other is going pushed the other way, every once in a while they'll slip. And that's the earthquake. And it may be over a relatively small region. But the reason we feel it is once you make the rock slip, it makes a wave travel through the rock. The shaking travels from one place to another. The shaking comes to the surface. When it hits us, that's what we call the earthquake. Most earthquakes we feel, unless you're standing right on the fault. I mean, you're standing on the fault right here, and suddenly it moves. Okay, that's your right field on the fault itself. Most earthquakes, what you feel is not the actual motion of the earth where it broke. That may be miles away. In Loma Prieta, 70 miles away. But then the wave comes. And this is typical. Whenever you shake something, you typically make a wave. When I shake the air, I make a wave. That wave reaches you. If you're standing close to me, it's very loud. That's because the wave hasn't had time to spread out very much. As you get further away, the wave is spreading its energy. This wave doesn't spread its energy. It goes along a straight line. And so you can see the amplitude of the wave doesn't change much. It goes back and forth. Eventually it dies down because it's losing energy to the air, to friction. But if it's going along a straight line, it doesn't lose much energy. If you want to talk to someone who is far away, and you want to just talk to them, talk through a tube. If you talk through a tube, and they still do this in some ships, as an emergency communication, they have tubes. Maybe you did it when you were a kid. You had a toy where you talk through a tube. It's wonderful. Someone can be there, 30 feet away, and you listen to the tube, and it's really loud. And the reason is the wave isn't spreading in the tube. It's just going in one direction. The reason things get quieter as you get further away, the reason I have to talk louder to talk to a whole class, is because the wave is spreading out. Typically, for sound, it's spreading out in basically 2 dimensions, up and down and left and right. And when it spreads out like that, it gets weaker, and it's an inverse square law. The reason for that is here's the energy, and I'm sending out this wave, and you're a certain distance away, it's spread out over the surface of this sphere. And the surface of the sphere has an area, which is, the area of a sphere is 4 pi r squared. That's the formula for the area of a sphere of radius r. So the energy is spread out over this much area. Go twice as far away, and it's the new r squared, r2 squared. If this is twice as far, that's 4 times as big. And so the energy is spread out over 4 times as much, which means it's 1/4 as strong at any place where you put your ear. So as you get further away, it gets weaker. Now, earthquakes, if they're going through the middle of the Earth, the shaking goes through the middle of the Earth, they're also spreading out up and down and left and right. And so they get weaker. But there are some earthquakes that travel on the surface of the Earth. They're just confined to the surface. They only spread out in 1 dimension. And so they tend to not get so weak. If you're confined to the surface of the Earth, you're not spreading out up and down, just sideways, then that's like spreading out on a circle. So here's the Earth, and here's your circle, and it's spread out over this distance, which is 2 pi r. And you go twice as far away, it's spread out over 2 pi bigger r. But if you're twice as far away, this is only twice as big. So if you're spreading out on a surface, it's not so much for the energy to lose. So keep this in mind. This is important for understanding earthquakes, and also for understanding what happened in Roswell, New Mexico in 1947. That when a wave spreads out completely like this, you get an inverse square law. You go twice as far away, it's 1/4. You go 10 times as far away, it's 1/100th as strong. But if it spreads out only on a surface, then you go 10 times as far away, it's only 10 times weaker. If it doesn't spread out at all, it maintains its strength on a line, like that. This is why the best kind of way to communicate is with a wire. Telephones. The signal doesn't spread out. It goes just to that one place. Now, there may be some losses because of friction, because of some heating, you're losing energy, but basically you're not making a signal weaker. It stays along a single line. We do this with fiber optics communications. We'll be talking about that next week. The trick of the fiber optics is you take a flashlight, and the light spreads out. Twice as far away, it's spread out to 4 times the area. So it's weaker. If you use a pipe to pipe the light, it doesn't spread out. That's why we use light pipes for fiber optics communication. You send light signals over thousands of miles by using light pipes. We'll talk more about those next week. The earthquakes that travel on the surface of the Earth tend to be the ones you feel at the longest distance, because their energy is just on the surface. It's not being spread out. The energy that goes through the bulk of the Earth spreads out in 2 dimensions. By the time you're 100 miles away, it's spread out so much that you don't feel it anymore. But the earthquake on the surface doesn't spread so much. It doesn't go up and down. It just goes sideways. And so the energy is confined to a narrow region. So now let's get back to what Maurice Ewing discovered about the oceans. Deep down under the ocean, you have molecules. Suppose you make a sound in the ocean. Now, Ewing had a clever idea for making a sound in the ocean. It was you take a metal sphere and you make it hollow. This hollow metal sphere will take a lot of pressure. You make the metal sphere, even though it's hollow, if you make it out of the right metal, you'll make it heavier than an equal amount of water. If it's lighter than an equal amount of water, it'll float. That's why wood floats. If it's heavier than an equal amount of water, it will sink and keep on sinking. So his idea was give the downed pilot a metal sphere, a hollow metal sphere, more dense than water. He'll throw it overboard, this thing will sink into the ocean, and it'll sink and sink and sink and keep on sinking. Now, as it gets under the water, you have the weight of the water above it. As it gets deeper, the pressure increases. The pressure gets greater and greater and greater. But a metal sphere is like an egg. I don't know if you've ever tried to break an egg. Well, you probably do by, you bang it against a corner. Interesting experiment for all of you to do. Put on a swimsuit or your birthday suit or something like that. Go into the shower. Take an egg. I really recommend you do this. Okay? Take that egg and put it between the palms of your hands. I should do this as a demo, but you wouldn't believe me. No sharp points, just smooth. And then push on the egg until it breaks and splatters. Okay, this is why you should do it in the shower or something like that. What you're going to discover, to your own amazement, is that the egg doesn't break. You may be unable to break it that way. It's very hard to do if you have nice, even, uniform force. An egg is a very strong structure. Even though the shell is so thin, when you push on it uniformly, the shell compresses. But only if you push on it in one place will it crack in and break. If you push on it uniformly, the shell compresses, it holds enormous strength. This is why little baby chickens are in eggs. Because the mommy can sit on it, and the shell isn't going to break. And you don't fully appreciate this until you go into the shower. Take a friend, have fun doing this. And try gently pushing on the egg with your palms. It's very strong. So Maurice Ewing's SOFAR spheres were the same way. You put them in the ocean, they're really strong. They don't break. You get deeper and deeper and deeper, and the pressure gets greater and greater. And finally, you get to the pressure that's greater than the palm of your hands. You get down. He designed it so it would break at a depth of about 1 kilometer, 1,000 meters. When it gets down there, it starts to break, and at that point, it's like an egg. Once you bent it and it's beginning to break, the thing goes catastrophically, and the enormous pressure brings it in. And in fact, what happens when it comes in like that is, bang, it makes a wave. So Maurice Ewing had invented a way for a pilot to take an egg, called a SOFAR sphere, drop it overboard, it would fall down, drop down, it would sink to about 1 kilometer, and when it got to a depth of 1 kilometer, the pressure was such that it would catastrophically collapse and it would make a loud noise. Basically, the water on both sides of this thing banging suddenly against each other would make a pop just like the clapping of my hands. A very loud pop because of the enormous pressure in this thing. So you'd make sound underwater. Now, water is like air. You move a molecule and you bounce it, and it will move the molecule next to it. And that'll move the molecule next to that, and so on and so on and so on. So you get a sound wave going. Whales sing to each other underwater. Actually, on the website, I have a link for songs of the humpback whale. So people really love this stuff. You didn't realize that the whales go, and people think, wow, this is really... waves are intelligent animals, and here they are singing to each other. And the whales had discovered something before Ewing did. They discovered that if you get down into the ocean, and you get down to a depth of 1 kilometer, if you sing your song, it doesn't spread out. It tends to stay. It's like moving along the surface, a 1 kilometer surface. It stays on that 1 kilometer surface so it doesn't spread out so much. That was a real surprise, but Ewing discovered that independently. Here's how it works. You get down to 1 kilometer, and you make this sound. And yeah, some of the sound goes up, and that actually does go up. Some of the sound goes straight down, that actually goes to, some of it goes horizontally, and that goes great distances. But the sound that goes at an angle is bent. The sound doesn't go in a straight line. What happens is it's bent like this, and then it's bent back up, and it's bent like this, and so on. And so the sound that goes at this angle is also bent. And the sound that goes at this angle is also bent. And so on. The sound that goes at this angle is also bent. And the result is a little of the sound that goes like this escapes. But some of the sound, about half of the sound, gets trapped into this virtual surface. And because it's trapped, it doesn't spread out as much. And because it doesn't spread out as much, it can go really long distances and still be heard. And this is what the whales had discovered. So when they sing their songs, they get down to this depth. And they start, whoo, 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 and they sing their songs better than I do. And the whales thousands of miles away can hear them. I haven't quite figured out what they're saying. You listen to it and it just sounds like they're singing, "Oh, what a beautiful morning," or something like that. But maybe they're actually conveying information. I don't know. I mean, I have lots of animals that do communicate, and if a bunch of wild dogs hunting, they communicate to each other, but they don't do anything we don't think they do anything as complex as we do, but whales are really smart animals. They have much bigger brains than we have, and so it's possible that they're sending information. We just haven't decoded it yet. Listen to it. Listen to the songs of the whales. But they're making use of the sound. Now, why is there a sound channel like this? This has to do with the behavior of waves in a way that I'll be getting to in a moment. It has to do with the way the waves will bend. Bending waves, the fact that waves don't always go in straight lines. Here it's going in a straight line. Here it's going in a straight line, but you know sound doesn't always go in a straight line. How do you know that? Because if you're on the other side of a door and you're down the hallway and I shout, you can still hear me. It sounds like the sound is coming through the door. It goes through the door and then it bends around. So waves have this property. You see them on the beach. Suppose you have some jetties here and the waves of the ocean are coming in. Then they spread out. And here you're getting a wave that traveled like this. It bent. So waves don't always travel in straight lines. In fact, you can actually bend a wave and have it travel. It's as if you're putting a force on the object. We'll talk more about that in a moment. I heard it this morning. There's a thing in the air that you can tell the wave is bending that I'll describe to you in a little while. But in the ocean, there are two things that make these things bend. One is the fact that as you're coming down, the water's getting colder. And the other is, as you're coming down, there's more pressure. And these work together to make, up here, a wave traveling horizontally is fast. Down here, a wave traveling horizontally is slow. And down here, a wave traveling horizontally is fast. As a result, the wave tends to bend. So no way I can move this up and still show it. So let me just bring this one down. Here's a feature of the way waves work. Imagine you're over an ocean, and you're looking down, and here is the crest of a wave. This is the crest. Crest is the high part of the wave. The low part of the wave we call the trough. And then there might be another crest. This is the hot part of the wave. And over here is the beach. As these waves are coming in, the direction they're moving is this. So the waves are moving this way. You're looking at the high part of the wave. You may notice that because of the shadow. You're looking from an airplane. You see the shadow of a wave. And so this is the high part of the wave, and it's moving like this. Now it gets to the beach. Over here it's shallow. And the shallow part may be this over here. So it gets to this part gets to the shallow part first. When that happens, this part of the wave slows down. In shallow water, the wave will move slower. One of the principles that turn out to be true for water waves. Could have been the other way around, but it turns out that in a shallow wave, the water moves slower. So what happens? This part of the wave slows down. And that means the crest of the wave tends to bend until it's coming in like this. So a wave tends to bend towards the slow direction. If this is the slow side, because the wave hits the shallow first on the bottom, here it may be deep, and here it's shallow, it tends to bend towards the shallow side. It tends to bend towards the slow side. Just imagine this wave coming in. This part slows down. It's like a marching band that are trying to stay in a line. And one side gets going slowly. And so the whole band, trying to stay in a line, starts walking in that direction. This is a fundamental principle that if you are a wave, and the wave is moving along, and one side slows down, the whole wave tends to bend that way. This is what Ewing discovered in the deep ocean. So colder and higher pressure down here actually made this move fast. Up here it was fast, but this was what became called the sound channel. And it was at a depth of about 1 kilometer. And it was a region where waves move slowly. Now look what happens. A wave, suppose the wave starts moving upward, like this. Here's a wave that's moving upward. The bottom part is moving slower, so the wave tends to turn and come on down. Now it's going this way. And now the bottom part's getting into the fast region, and the upper part's in the slow region. So this part slows down, and the wave goes like that. And so the wave tends to get trapped in the sound channel. And because of that, it doesn't spread out very much. And because it doesn't spread out, it can be heard for long distances, which is what the whales discovered, and then one day Maurice Ewing discovered. So here we have under the oceans. This was a great secret during World War II. Why is that? Suppose there's a submarine in the sound channel, and it's running its propeller, chugga, 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 chugga. And it's making sound. Some of that sound will come up to the surface, but a lot of it gets trapped in the sound channel. And if it's trapped in the sound channel, you can hear it 1,000 miles away if you put a microphone in the sound channel over here. So Ewing's idea was to put some microphones in the sound channel, to give the pilots these SOFAR spheres. They drop them in the water. When they get down to this depth of 1 kilometer, they go boom. They emit a sound. Some of the sound goes straight up and down. That's lost. But a large fraction, of about half the sound, gets trapped in the sound channel. It only spreads out over a surface. So it's not inverse square. It goes twice as far away. It's only half as loud, not a quarter as loud. So this travels in the sound channel, and you can hear it thousands of miles away with a microphone. Okay, so here you are. You have a microphone. And you hear ping. Say, whoops, we have a soldier, we have a pilot down in the water. He just released a SOFAR sphere. What do you do with that ping? What you need is more than one ping. Suppose the pilot is right here, and you have 1,000 miles away. You have a microphone here, another one here, another one here. This one you'll hear it first, because that's the closest. Then you get this one and this one. If you know the distance to 3 of these microphones, you can tell where it is. What you do is you look in here when the sound comes in. If the microphones are all equidistant, the sound would all come in at the same time. You know it's in the center of the circle. Not hard math. If they're not equidistant, you just listen to when they come in, and you can find the unique location where the sound would have reached those microphones in that order with that spacing. And that's what he did. You put down these microphones at various places. He had them on the Hawaiian Islands. And if you hear this ping, you know where the pilot is. You send an airplane there. But the marvelous thing is, if you found one of these spheres, you wouldn't think it was a secret anything, because it only works because of the sound channel. End of World War II. Maurice Ewing thinking about the atmosphere. And he realizes there's a sound channel in the atmosphere. How does he realize that? I felt really stupid in 1995 when I read all of this. The reason is, I knew all the physics. Why did I never realize there would be a sound channel in the atmosphere? Here's how it works. For sound, as we learned in Chapter 2, the sound goes roughly the speed of the molecules. If you have molecules bouncing around, this one doesn't even press against this one until it gets there. In gases, not true in solids and liquids, the speed of sound is approximately equal to the speed of the molecules. In solids, it's faster, because solids are touching each other, and the push can go right away. But in gases, the molecule has to get over there. So you give this one a little bit of extra energy. You wait till it gets over there. The speed of sound is about the speed of molecules. That's about 1 mile every 5 seconds, which is the number for estimating how far away the lightning was, right? Lightning, the light gets here right away. You start counting seconds. If the sound gets here 5 seconds later, that means it was a mile away. Sound goes about 1 mile every 5 seconds. In water, it goes about 1 mile a second. That's because the molecules are already touching each other. In rock, it goes even faster, 3 or 4 miles in a second. So sound is slowest in the air, about 1 mile every 5 seconds. Water, it's 5 times faster, 1 mile a second. Rock, it's even faster than that. Now, suppose you have hot air. In hot air, the molecules are moving faster, and so the speed of sound is faster in hot air. Just because the molecules are moving faster, because that's what heat is. Heat is the speed of the molecules. It's the kinetic energy of the molecules. Absolute temperature is the energy per molecule. So let's take a look at the atmosphere. Here we are in the ground. And sometimes it's pretty warm down here. But as you get up higher, it gets cool. Just because expanding air, if the wind happens to blow some air up, the air expands. When the air expands, it gets cool. So you get cool air up here. But if you get high enough, you get to the ozone layer, and then it gets warm again. Warm because of the ozone. The ozone absorbs the ultraviolet radiation from the sun, protects us from the ultraviolet radiation of the sun, but makes this warm area that's called the stratosphere. If you watch a thundercloud, it rises because it's hot. As it gets up, it cools, but the air is even cooler than it, so it keeps on going until it gets up to the ozone layer. Now it's surrounded by warmer air, and so it's cooler because it's been expanding. It doesn't rise anymore. This is about how far the thunderheads go. If you want to know where the ozone layer is, watch a thunderhead. And when it gets up there, it's not easy to see in Berkeley. We don't get that many thunderheads. But if you go out to the Sacramento Valley or go up in the mountains and you watch the clouds go up and then they stop, that's where the ozone layer is. We'll talk more about this when we get to invisible light, because it's the ultraviolet light coming from the sun that creates the ozone layer. The ozone then absorbs the ultraviolet light, prevents the ultraviolet from coming down here and giving us skin cancer, and at the same time warming up this upper part of the atmosphere. So here's the structure of the atmosphere. Warm, that's where sound travels fast. Cool, that's where sound travels slowly. Warm, where sound travels fast. Just like in the ocean. If you have a wave, a sound wave that starts to go up this direction, here's the wave traveling. The bottom is slowed down because this is getting into the fast part. And so it bends. And the wave, you'll trap sound in the sound channel. And so it doesn't spread out. So if you want to actually make a sound that's heard around the world, the best place to go is up in the sound channel. Now, if birds were as big as whales, maybe they would do this. They go up to the sound channel and go, chip, 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 and the sound would go around the world. We know of no animals that make use of this sound channel, except for Maurice Ewing. His idea was the following. Basically 1945, the U.S. has exploded a nuclear bomb. A nuclear bomb is you get this explosion, then you have this very hot amount of air, very, very hot. Because it's very hot, it starts to rise. That's what we call the mushroom cloud. But some hearts are hotter than others, so this thing is very turbulent. A nuclear bomb first have the blast, then you have this really turbulent hot air that makes a roar. So the initial sound may be very loud, but then you have this roaring sound because of the hot, turbulent air that's rising. When this hot air gets up to the sound channel, it's making a lot of sound. When it gets to the sound channel, that sound will not spread out as much. It will basically travel around the sound channel for thousands of miles. So what use is this? It's not loud enough to do any damage. Well, back in 1945, the United States was seriously worried about the Soviet Union. We knew that they were building a nuclear bomb too. How could we tell when they succeeded? Ewing's idea was, let's go up to the sound channel and listen. See, back then we didn't have spy satellites. We didn't even have spies. Stalin was very good. If he had anybody who was indirectly, mildly suspected in some way of not being completely loyal, he simply killed them. Very hard to be a spy under Stalin because he had such a low threshold for slaughtering you. So we didn't have any spies there. We couldn't know what was going on. If you just sort of looked funny, he would kill you. I mean, he killed 30 million people. 30 million people killed by Stalin. So, no spies, how do you find out? You listen. If he makes a nuclear bomb, by the time it gets up to the sound channel, just below the stratosphere, this sound will travel around the world. So this was Ewing's idea. Let's put some microphones in the sound channel. Now, this was a highly classified program. It was about as classified as anything got back in 1945 because it was relating to nuclear weapons. And we didn't want the Russians to know that we could listen in to their nuclear weapons tests. We could tell where they were by how the sound arrived from different directions. So we would know the location where they were testing them, just like we knew the location of the pilot from his SOFAR spheres. You put these microphones up at various places around the world. So we can get all sorts of information. We didn't want them knowing about this. So it was highly classified. It was classified along with nuclear weapons. Now, to put a microphone up here, we're talking about putting microphones up at the top of the thunderheads and keeping them up there for long periods of time. Moreover, they have to listen, so you want it to be a quiet environment. So he had this idea that you would put it up with balloons. It's a natural way to do it. You require very big balloons to be able to keep the microphones up there that long. At that time, the world's expert in high-altitude balloons was a fellow named Athelstan Spilhaus, who later became a good friend of mine, and he was involved in this. He designed the balloons that would carry up these microphones into the sound channel to listen. The project was called Project Mogul. And I knew Spilhaus for years. Project Mogul, very highly classified. He never told me about it. In fact, it got shut down after 5 or 6 years because it turned out there was a better way to detect nuclear explosions. Earthquakes. When you explode a nuclear bomb, it makes the earth shake. That sends a wave through the earth. Now, a key thing about earthquakes is most of them, they take place underground. The ones we had here last week were 5, 8 miles deep. But a nuclear explosion is on the surface. So you can detect that. It's also a little bit different from an earthquake. A magnitude 6 earthquake, we'll be talking about magnitudes, gives about the same energy out as 1 million tons of TNT equivalent nuclear bomb. A big nuclear bomb. A magnitude 6 is like a big nuclear bomb. We had last week was really quite tiny. But a magnitude 6, magnitude 7 is like 30 nuclear bombs. That's what we had in Loma Prieta in 1989. So these make the earth shake. The shaking travels. You can detect it on the other side of the earth. This eventually put Project Mogul out of business because it was so much easier to detect these little earthquakes. And you could tell where the bombs were from the earthquakes, too, by looking at the waves coming to different locations around the world. Looking at the time when they arrived, you can tell precisely where the nuclear weapons were being tested. So eventually we used earthquakes. In fact, the whole science of seismometers was really advanced by the U.S. need to put very sensitive earthquake detectors. So we built these earthquake detectors all around the world. In fact, during the Cold War, we were rapidly building earthquake detectors. We were putting microphones underneath the ocean to find submarines. That became a huge project. The submarine detectors, the microphones put all around the world, was called the SOSUS array. S-O-S-U-S, sub-ocean surveillance, something like that. SOSUS was one of the most highly classified bits of information of the Cold War, the SOSUS way. We spent billions of dollars on the space program and more billions of dollars putting microphones under the ocean. More than on the space program. And nobody knew about this until Tom Clancy wrote his book, The Hunt for Red October. This is why you should read the book, not to see the movie is all about adventures, you know, and so on, and capturing this guy and having him, you know, a great story. I'm not going to give it away right now. But in the book, he talks all about how the SOSUS array works, how the submarine captains were trying to avoid the sound channel. And everybody who knew about the subject, including me at the time, looked at this book and said, my God, he's giving away all of our secrets. Fortunately, he makes some mistakes. So not all of the book is accurate. But it was accurate enough that the people in the Navy, when someone comes into the Navy and they had to learn about the SOSUS array, you know, how do you teach them this? You have to have a, you know, physics for future submarine commanders, in which you spend all your time learning about the SOSUS array. Well, they found an easier thing. They would say now, and they still do this, they say, you're in the submarine service? Here, read Tom Clancy's Hunt for Red October. Okay, this is the best introduction to what is really going on in submarine warfare that you'll ever get. Then, of course, at the end of the book, they'll say, now he got a few things wrong, let's correct those, which is something I'm not going to do here. But most of it is right. So that became an essence of the Cold War, the SOSUS arrays. The huge numbers of seismographs put around the world to detect the earthquakes induced by atomic explosions became the primary way of checking for nuclear explosions around the world. There were other ways. When we got satellites up, we also watched for them from space. Very interesting story there, because I got deeply involved in one such event, on analyzing such an event. It's an interesting story. But in 1945, Project Mogul was to take these microphones. Now, the best microphones they had, you'll see this in old movies. You watch the movie Aviator, and you'll see the movies they had. Microphones then were high-tech, and they were difficult. And the problem was when you have a microphone, you put it on a stand, and little vibrations of the ground and the stand would be picked up by the microphone. It was called microphonics. If you have a microphone that's attached to something, it's sitting on the table, it picks up these microphonics, and you're getting all these vibrations and squeals and noises and so on. So what they had to do is suspend the microphone. What they'd do is they would take the microphone and have a delicate wire coming out of it to carry the signal, and they'd suspend this on springs. And you'll see this in the old movies. And they'll put the spring on a disc like this. And then this is the disc microphone. So this kind of disc microphone was the high tech of 1945. And what everybody used, you look at old pictures, you'll see these old disc microphones. Now we have much better ways of doing it, but the suspension on springs like that. So Ewing flew these disc microphones from my friend Athelstan Spilhouse's balloon up into this area where the sound layer was, and he would fly these balloons. Where do you fly them from? Well, you know, this is all highly classified. What is being done with these balloons? Well, we're detecting nuclear explosions. It's all classified. We don't talk about that. There was only one location in the United States where you could do the following two things. One was a place where you could have nuclear weapons secrets. Because this was the place where our nuclear bombers were based. This is where they kept the nuclear bombs. This was the Army Air Base in Roswell, New Mexico. It's where our nuclear weapons were basically based for the Strategic Air Command. You should all see the movie Dr. Strangelove to get a sense of what that era was like. A truly great movie. The Strategic Air Command would carry these weapons and be ready. They'd be in the air all the time because we were always worried that our base would be bombed. And then we couldn't retaliate. So we had planes in the air at all times carrying nuclear weapons where the president could send a signal to the plane, go bomb the Soviet Union. This is what the movie Dr. Strangelove was about. It was really people look back on nostalgia with the 1950s. I can't believe it. I mean, here you are, when you have nuclear weapons in the airplane at all times, all set to bomb the Soviet Union if they get the secret signal from the president. And people look back on this era with nostalgia. This is the era when we would have take cover drills And you ask kids, what do you worry about at night? And they'd say, oh, a surprise nuclear attack by Russia. This is the wonderful 1950s. Believe me, you're much better off today. Okay. So Ewing was listening with these balloons, these large balloons, these were much larger than weather balloons. And they had, I have the images of these things. They're on the website. You can look at them. These huge balloons with long strings of microphones that would hang down. So you have this huge balloon, hundreds of feet in diameter, strings of microphones hung down. They had special reflectors on them so that people could locate it, so that the people who were running this would be able to locate exactly where that balloon was. Because when the sound signal arrived, they had to be able to tell the direction it was coming from. And to do that, they had to know the position of this. So they had special radar reflectors on it. We'll talk more about those. So this thing would hang from the sky with these microphones and would send radio signals back down when the microphone picked up anything, and indeed they picked up the first nuclear test of the Soviet Union. So this was a successful program until it was displaced by the seismic detection signal. One of these huge things crashed in 1947 outside of Roswell, New Mexico. And the people, the Air Force, put out a press release saying that our flying disc microphones had crashed. Actually, from the jargon of the day, they just called them flying discs, it turned out. It's sort of like calling a radio receiver a radio, or a microwave oven a microwave. They were calling these things the flying discs. And they announced that the other flying discs some flying discs had crashed when they recovered them, was picked up by the newspapers as flying saucers. That's how they interpreted it. Now, the guy who announced that this classified program with the flying disc microphones had crashed got into big trouble, and they immediately retracted the press release and said, no, it was just a weather balloon. It was a lie. Interesting issue. Should the government ever lie to its own people? Back then, they made the considered decision that the right thing to do was to lie, because this program, you think back why it really required so much secrecy. Was there some way the Soviets could have hidden this kind of a test if they knew about it? I think the worry was more that they would pick up on our tests. I'm not sure, but it was a highly classified program. Some information had leaked out, so they countered it with a lie. And this was done on purpose. The records have all been declassified, including long interviews with my friend Athelstan Spilhaus describing the program and so on. The remarkable thing about it is that although I knew about the seismic detection of submarine of nuclear weapons, I knew all about the atmosphere, but in 1995 I had never put them together to recognize that one could detect nuclear explosions through the sound channel in the atmosphere. I just never thought of that until it was actually several senators who insisted that the government publish this stuff and declassify it. Now there are all these huge documents describing this. When it came out, my reaction was, oh, am I dumb? Why didn't I think of that? Of course. The sound channel in the atmosphere. Some people, and maybe some of you, think right now that what I'm doing should have worn my black shirt so I could be the man in black. What I'm doing is giving you a wonderful cover story to try to convince you that we don't really have flying saucers that we captured in Roswell, New Mexico in 1947. And boy, didn't I come up with a great story to try to convince you was actually a system to detect nuclear explosions. Ha ha ha, did I fool you on that? Well, I don't think I could come up with such a great story, because the sound channel in the oceans, the sound channel in the atmospheres, the fact that this really does work is such an amazing bit of physics. And of course it would work. As soon as I heard it, I knew it would work. And so the fact that this was what it was designed for, it must be. Nobody could have come up with that great a cover story. But of course, Roswell, New Mexico now has a booming economy from people who go to see the site where the classified flying saucer story really happened. And there are all sorts of people who are really, look at the movies, you look at the X-Files, all the stuff about Roswell, New Mexico. For those of you who haven't heard about Roswell, New Mexico, do a web search on Roswell flying saucers, and you will be astonished by the 13 billion hits you'll get of people talking about what really happened in Roswell, New Mexico. Anyway, it's a fascinating story. Since 1995, the story has been written up in many magazines what really happened. I've just given you what really happened. But, of course, I may be lying and just trying to cover what's the story of the UFOs who are now collaborating with us and actually living here in parallel with us, these aliens, and I'm just not allowed to tell you that I am an alien or something like that. Anyway, that's the story of Roswell, New Mexico. This bending of sound in the atmosphere is something that I experienced this morning. Here's how it happened. I pointed it out to my wife. In the morning, what happens sometimes is the sun comes out for a little while. The air is cool. And then the sun comes out in the morning and starts to warm up the ground. This morning it didn't do that. This morning the ground was extra cool and the air was a little bit warm. That's called an inversion. Normally, as you go up in altitude, it's cooler. But once in a while, you get an inversion. Sometimes this happens because warm air comes in. Sometimes it happens because of smog. This morning there was an inversion, and the way I can tell is very simple. Let's compare this. In fact, let me draw two diagrams. The usual condition, where it is cool and warm down here. And here's the ground. And here's a train or a truck making noise. And the noise comes out from the truck. Now imagine this wave. Here's the crest of the wave coming out. Warm, it travels faster. Cold, slower. So it tends to bend. Here it's coming. It goes faster down here. It bends upward. The sound normally bends like this. That's the normal direction of sound travel in the normal atmosphere. If there's an inversion, which means warm air up here, then here's that train blowing its whistle or the truck, and the wave starts coming up. And look what happens. Here's the crest of the wave coming up. And it's slower here and faster here. So the wave tends to bend like this, and the sound will actually come like this. And here am I. There's my ear. Listening, I can hear the distant sound. Here I don't. I'm here and it's a quiet morning. The distant sound bends away. I don't hear distant sounds. But when I can hear that distant sound, then I know there's an inversion. And I heard those distant sounds this morning. When there's an inversion, that usually means there's warm air up above. As the ground heats up, normally when ground heats up, it rises. And the air gets, we lose the hot air. But when there's warm air above, it can't rise because this air is already warm. Because it's warm, it's expanded. Because it's expanded, it's not very dense. And so when this air comes up, there's less dense air here. It tends to fall back down. When you have an inversion, it's going to warm up the ground, real warm. So in the morning, when I listen and I hear these distant sounds, I don't have to listen. I wake up and I hear these distant sounds. I know there's an inversion. That means the sound is bending back down. I'm hearing the sound of the train down by the bay. I know now it's going to warm up during the day because there's an inversion and the sound is coming back down instead of rising up like that. I used to notice, another time you notice this is in the evening. Think about, every now and then if you're on campus, you may hear the sounds of the train down by the bay. But odds are, if you hear that, it's in the evening. In the morning, you don't hear them. Today you did, but most mornings you don't. The reason is, in the evening, the air is heated up during the whole day. The ground tends to cool first. We'll talk why next week. Why the ground tends to cool first before the air. So in the evening, you frequently have an inversion. The evening inversion. And the result is a distant train all the way down by the bay. the sound will tend to come down. You'll hear the distant sounds in the evening. I used to notice this when I lived a mile from the beach. And you'd wake up in the morning, and you couldn't tell if there were waves or not. This is on the East Coast. You wouldn't hear a thing. It would be quiet. But then at night, after the sun went down, the ground was cooling very rapidly, you would hear the beach, even though it was a mile away. You'd hear the crashing waves. It was quite dramatic. I don't know if you ever go backpacking or if you go on a lake, you'll notice the same thing. At night, you're going to hear these distant sounds. So be on the alert for this. We're going to be talking more about the sound channel, and on Thursday about music.